Okay, this is part 2 of our lesson on finding the roots of polynomials, and I'm about to show you a theorem that we're going to use for narrowing down our options, but I don't want you to write what you see on this screen, so just put your pencil down and watch what I do. So I'm calling the process of finding the roots of a polynomial the root chase, and so we want to narrow down the root chase. And what we're going to do is look at some patterns that we see from quadratics and then see if we can generalize those to other polynomials. So let's say I have these 3 examples. These are all quadratic equations and I'm going to find their roots. So these all happen to be factorable, so I've factored them, and then I'm going to set each factor equal to 0 and then solve each equation. And we have these roots. So the point of what I want to do today is show you how these roots relate back to the numbers in the problem. So if you look at the numerators of the roots, so here we have -7 and 1, where do those numbers actually come from the original problem? If you trace back through the steps, you'll see that those numbers come from here, the constant. And if we think about the other 2 examples, the numerators of 2 or -2, 5, those numbers came from the constant as well. Those are factors of the constant. Same thing here, -9 and 4 are factors of -36. Then what about the denominators? So 3 and 2, where did they come from? They came from factors of 6, the leading coefficient. And that's the case for all of these. The denominators are going to be factors of the leading coefficient. So, if you have a polynomial that you're trying to find the roots for, and if you want to find the rational roots, meaning the roots that are fractions, it will always work out that the numerators have to be factors of the constant and the denominators have to be factors of the leading coefficient. Now, that only narrows it down. That doesn't tell you exactly what they are because, of course, if you take a look at number 3, 36 has a lot more factors. You don't know that it's going to be -9 and 4, or even maybe +9 and -4. Couldn't it be 6 and 6, or 18 and 2, or something like that? So there's options, but we've narrowed down the options. So this is called the rational roots theorem or the rational zeros theorem, and you should write this down. If P over Q is a rational number, so a fraction, written in lowest terms, and if P over Q is a 0, meaning a root of the function f, which is a polynomial function with integer coefficients, then P, here's the important part, P is a factor of the constant term. So the numerator is a factor of the constant term, and Q is a factor of the leading coefficient. Q is the denominator. So numerator over denominator comes from the constant over the leading coefficient. Okay, so here's how we use the rational roots theorem. We use it to make a list of all possible rational roots for the polynomial, and then from that list we find the roots. And the list of all possible rational roots I call the APRR list. So here's how we start. To find the potential numerators, we list all of the factors of the constant. And it could be positive or negative, so we put a plus or minus in front. Now I just put the plus or minus one time to count for all of them instead of writing plus or minus every single time. So the factors of 20, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20. And then the denominators are going to be the factors of the leading coefficient, plus or minus any factor of the leading coefficient. And for this problem, the leading coefficient is 1, so all we have is plus or minus 1. So for the APRR list, we put together all the combinations possible of those numerators and those denominators. This one's fairly simple because we only have plus or minus 1 for denominators. So we have plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1, plus or minus 5 over 1, 10 over 1, 20 over 1. So what we're saying is, if we were looking for rational roots for this polynomial, our only choices are these 12 numbers. We've narrowed it down. And then what we would do from there is we would start trying synthetic division with these numbers until we found the roots. We're not going to do that on this. Oh, we are. We're going to find the roots. Okay, so let's try some synthetic division. Okay, so let's try 1. Let's see if 1 is a root. So I'm going to put 1 in the box, and then we have our coefficients 1x cubed, 5x squared, negative 4x, and negative 20. Bring down the 1, multiply by the number in the box, write it down and add. Multiply by the number in the box, write it down and add. Multiply by the number in the box, write it down and add. The remainder is negative 18, therefore we don't have a root. Let's try negative 1. Same thing. Bring down the first number, multiply by the number in the box, write it down and add. Multiply by the number in the box, write it down and add. Multiply by the number in the box, write it down and add. We get negative 12 for the remainder. We don't have a root. We're looking for 0 for a remainder for it to be a root. Let's try 2. Bring it down, multiply, add, multiply, add, multiply, add. Yay! We got a remainder of 0, which means we do have a root. So x equals 2 is a root. And there's actually more information that we get out of this problem because remember what's left here is represented by 1x squared plus 7x plus 10. If we set that equal to 0 to find the remaining two roots, turns out that that factors into x plus 2 times x plus 5. And then if we set each of those equal to 0, we find that the other two roots are also rational. They are negative 2 and they are negative 5. So we have all three roots. It turns out for this problem, not every problem, but for this problem, all three are rational numbers, and notice they're all in the APRR list, positive 2, negative 2, negative 5. So let's try this again. Here's number 2. Make the APRR list and find the roots. Okay, so let's find our possible numerators, which would be factors of the constant. So factors of 1, just plus or minus 1. Let's find the possible denominators. So these would be factors of the leading coefficient, which is 2, so plus or minus 1 and plus or minus 2. Oh, we got a lucky break this time. We have a short APRR list. Plus or minus all of the numerators divided by 1, so just 1 over 1, and plus or minus all of the numerators divided by 2, so 1 over 2. So we have 4 numbers in this list. So let's go ahead now and start trying them to find roots. Let's try 1. We have the coefficients from the polynomial. We can do synthetic division. Bring down the 2, multiply, add, multiply, add, multiply, add. Right off the bat, we get a remainder of 0. So x equals 1 is a root. And then from here, we have 2x squared plus x minus 1. We can set that equal to 0. Let's see if that factors. We might as well try it. Looks like it does. So if we set each of those factors equal to 0 and solve each one, we end up with x equals 1/2 and x equals negative 1 as the other two roots, and those are all in the APRR list. We have positive 1, we have negative 1, and we have positive 1/2. Okay, now for this one, when you look at the problem, you can anticipate that there's going to be a long APRR list because we have 24 and we have 4, and those have a lot of factors. I'm going to show you a way to consolidate your synthetic division into a chart. Synthetic division is already a shortcut, but it's like I'm showing you a shortcut for your shortcut, and it's a way to organize it all together and take up less space. And it will be very critical to understand the chart in order to move forward in this unit and be able to do the more difficult problems. So we're going to start the same way as we did on numbers 1 and 2, which is to make our list of numerators. So these would be the factors of the constant. So plus or minus 1, 2, 3, 4, 6, 8, 12, and 24. Those are all the factors of 24. And then for the denominators, all the factors of 4, we have plus or minus 1, 2, and 4. So then the APRR list, we have to be pretty organized about this so we don't miss some. Here's how I like to do it. First of all the numerators over 1, then all the numerators over 2. So 1 over 2, 2 over 2, but that's just 1 and we have it. 3 over 2, 4 over 2, that's just 2 and we have it. 6 over 2 we have, 8 over 2 we have, 12 over 2 we have, and 24 over 2 we have. So we're done with 2. Now we use the denominator 4. So we have 1 over 4, 2 over 4 we have, 3 over 4 is new, 6 over 4 we have, and 8 over 4, 12 over 4, and 24 over 4 we have. So here's our list. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times 2, 24 possible rational roots, and we're going to figure out which ones are actually rational roots. So I'm going to show you now the chart method for synthetic division. So what you do is you leave yourself plenty of room to make lots of rows of synthetic division, and in the middle you're going to make a 0 row. This would be as if you're dividing by x minus 0, and these are the numbers you would have left. You would have the numbers that are from your problem. You would have 4x to the 4th, 0x cubed, negative 45x squared, 70x, and negative 24. But if you divided by x minus 0, negative 24 would be your remainder. So I'm going to split that off into a remainder column. Okay, next, let's say you want to try x equals 1. So it's like putting 1 in the box when you write it there. And you know how after you put a number in the box, you always bring down the first number? So here we are bringing down the 4. Actually, I brought it up. 4 times the number in the box would be 4 times 1, plus the next number 0 would be 4. Now that 4 times the number in the box is 4, plus the next number is going to be negative 41. Negative 41 times the number in the box is negative 41, plus the next number is 29. 29 times the number in the box is 29, plus the next number is 5. So the remainder is 5, so we do not have a root. But we did save a lot of space by just taking up a single row for that synthetic division. Now suppose we try 2. Okay, every time you do a new synthetic division, you have to use the 0 row. So that's why I drew lines around it, and you can use a highlighter or something every time you go back to those numbers. Bring up the 4, multiply it by the number in the box, and the number in the box is now 2. 4 times 2, add the next number in the 0 row. So 4 times 2 plus 0 is 8. 8 times 2, add the next number in the 0 row. I'm going to grab my calculator. I don't want to do all this in my head. So 8 times 2 plus negative 45, and that's negative 29. Negative 29 times 2 plus the next number in the 0 row, which is 70, and that's 12. 12 times 2 plus the next number in the 0 row, which is negative 24, and we get a 0. So that's great. Now we have a root. So x equals 2 is a root. This particular problem has 4 roots though. And so we need to keep going and searching with synthetic division until we find one more. So I could try 3 next. I could try some negatives. I'm going to go ahead and try -1. So I want to show you how you do the negatives. So you put it down below the 0, bring down the first number, multiply by the number in the box, that's -4, add the 0, and you get -4. Multiply that by the number in the box, now we have +4, add -45, and now we have -41. Multiply that by the number in the box, now we have 41, add the next number 70, and we have 111. Multiply that by the number in the box, we have -111, add the -24, and we have -135. So that's not a root. Now, don't despair when you find things that aren't roots, because remember, we're pretty close to the point in this unit when we're going to graph these things, and the remainders are also the y-coordinates of the points, so these are just points we could graph. We could graph the point -1, -135 on our graph. Let's try -2. Bring down the 4. Multiply by the number in the box, we get -8. Add the 0, we get -8. Multiply by the number in the box, we get 16. Add the next number, -45, and we get -29. Multiply that by -2, and then add the next number, 70, and we get 128. Multiply that by -2, and add the next number, -24, and we get -280. Well, that's a bummer. So what I'm going to do is pause, and then I'm going to go ahead and fill in a few more rows. Okay, you see I've done a few more rows, and it actually took quite a while to get to another root. It looks like -4 is also a root because we got a remainder of 0 there. So on the bright side, it was good practice with synthetic division and good practice with making the chart. I would advise you, if you're confused about the chart, to not do this. Oh, I understand regular synthetic division, but I don't understand the chart, so I'm just not going to do the chart. Please don't do that. Instead, you need to learn how to do the chart. I have a tutorial video for you tonight, and I'm also happy to help you in person with doing the chart, because you're going to learn some things through the chart that you wouldn't otherwise learn about these problems if you're not doing it. So just trust me here. I've taught hundreds and hundreds of students in the last 100 years how to do this. And so you'll have to trust me. Even if it seems like a lot of work right now, it will save you some headache later. Now, you might have noticed that we still only have 2 roots, and let me give you another bit of information about how to find the final 2 roots. So, if you think about this, let's say I take the numbers that I had left over from dividing by 2. Those numbers would represent a cubic, 4x cubed plus 8x squared minus 29x plus 12. Well, now that I know the problem is divisible by -4, I can do synthetic division and divide -4 into the cubic. -4 divided into the cubic, the remaining cubic. I know it's going to go in evenly because we found that it was a root of our problem. So we just have to figure out what these numbers are. See, it went in evenly, we got a 0, and these numbers represent a quadratic. 4x squared minus 8x plus 3. So from there we can set it equal to 0 and find the remaining 2 roots. So I call this process whittling it down. Once you have found all but 2 of your roots, you can divide the ones you know into the rest, and then that will whittle it down to a quadratic. And then once we have this quadratic, if it factors, that's cool. I think this one does. Yep. If not, you would use the quadratic formula. So this one happens to factor. Set each factor equal to 0. And then here we have our 4 roots. We have, I'll put them all together. X equals 2, -4, 3/2, and 1/2. And those were all numbers that were in the APRR list, you might recall. Okay, 2, -4, 3/2, and 1/2. And there's something else I want to show you. So I'll talk about this more later, but notice how our remainders here went from positive to negative. They're going to go from positive to negative by passing through 0, And so it makes sense that there was a 0 between 0 and 1, and that was 1/2. Okay, so let's move on. Here's the homework. You'll notice there are not very many problems, but these are going to take you a while. This is a lot to do in a single problem, and it's going to take some time to adjust to these strategies. So just be patient. I have given you video tutorials for almost all of it, and the video tutorial for number 39 helps you understand how to make the synthetic division chart. So in case you need to walk through that process again, it's all described right there. Let me know also if you have questions that you want my help with. Thanks, everybody.